Welcome back to Energy Conversion System 1. In this video, we are going to talk about an introduction to thermofluids in fluid machinery. There will be 5 sections in this video. We will start this video by talking about the properties of fluids, and then we will continue with fluid statics and fluid kinematics, fluid dynamics, and thermodynamics process in fluid machinery. Properties are a set of quantities that differ one fluid to another. To quantify and differentiate one fluid to another, there are at least 9 properties of fluid that we need to understand. They are density, specific volume, specific weight, specific gravity, viscosity, surface tensions, bulk modulus of elasticity, speed of sound, and vapor pressure. Density represents the ratio between mass and volume. In Greek letter, normally we wrote them as rho. Density normally characterizes mass of a fluid system. In International System of Units, density has a units of kilogram per cubic meter. Density of a fluid differs to another fluid. For example, if we take gas, the density of gas normally depends on the pressure and the temperature of the substance. On the other hand, for liquid, the density of liquid only has a small variety over temperature and pressure. On the other hand, specific volume, or normally symbolized as small v, is the opposite of density. It is the ratio between volume and mass, and it has a unit of cubic meter per kilogram. Specific volume is normally being used or mostly being used in a thermodynamic process instead of fluid mechanics or fluid dynamics process. Specific weight itself, or normally symbolized as gamma, is a ratio between weight and volume, or equal to mass multiplied to the gravity and divided by volume. Therefore, it has a units of Newton per cubic meter. Specific weight is normally being used to analyze or represent a weight of a fluid system. Specific gravity, or normally written as G, defines a ratio between a density of a fluid to a density of water at a certain temperature. Normally, the temperature that being used as a reference for specific gravity is at 4 degrees, where the density of water at this point is equal to around 1000 kilogram per cubic meter. Therefore, mathematically, we can note down that Sg is equal to density, let's say, of any fluid divided by density of water at 4 degrees Celsius. Up to this point, now we know that these 4 quantities are related one to another. So therefore, if we know a density of any fluid, we can get the specific gravity of that fluid. Or if we want to know the specific volume of that fluid, we can get it from the density. Or on the other hand, we can get the specific weight of a fluid from the density of that fluid. Normally, in our daily life, we define viscosity as a thickness of any liquid. For example, if we pour down a syrup from a bottle to a glass, to an empty glass, for example, it will take more time to fill up that glass compared to if we pour water to that glass. So water will fill up that glass faster than the syrup. If we look from the physics point of view, we can define viscosity, or in Greek letter we normally write it down as mu. It can be defined as a degree of resistance from any fluid to deformations at any given zero rate. So if we go back to the example between syrup and water, we can simplify that syrup has a higher viscosity than water. There are two types of viscosity. The first one is the kinematic viscosity, and the second one is the dynamic viscosity. The dynamic viscosity, or mu, is a ratio between shear stress, or tau, written with a unit Newton per meter square, to the shear rate of the fluids, or written in du per dy. So this is the velocity gradient of the fluid, and it has a units of 1 per second. So therefore the dynamic viscosity has a unit of Newton seconds per meter square. On the other hand, the kinematic viscosity, or in Greek letter written as nu, is the ratio between dynamic viscosity, mu, divided by density, and it has a unit of meter square per second. Viscosity itself is a temperature dependent property. Generally, for liquid, the viscosity will decrease as the temperature increases. On the other hand, for most gases, the viscosity will increase with an increase in temperature. When we talk about surface tensions, normally these three images came up shortly right after that. So we can see an insect floating on water, or a coin that stays on the surface of water, coin or paperclip that remains on the very top surface of the water. We know that this object floats on the top surface of the water due to it owns a higher density compared to the fluid itself, or in this case water. These objects, let's say coins or paperclip, float on a water surface without becoming or even partly submerged into the water. Surface tension itself can be attributed to cohesions and adhesions between molecules. Moreover, the surface tension itself normally use a symbol of sigma in Greek letter and has a unit of Newton per meter. The bulk modulus of elasticity is a property that can be used to characterize the compressibility of a fluid. Normally it is written as EV, and it has a unit of Newton per square meter. Mathematically, the bulk modulus of elasticity can be written as the ratio minus of the ratio in pressure change divided by change in volume per initial volume, or it equals to pressure difference or change in pressure to the change in density divided by the initial density. From this set of equations, we can see that a fluid that owns a high bulk modulus of elasticity can be categorized as an incompressible fluid. It means that it will take a big change in pressure to give us a result in a small change in volume. So that defines the incompressibility of a fluid. So it will take a big amount of change in pressure to give a small change in volume. For example, at atmospheric pressure and temperature of 16 degrees of Celsius, let's say water requires a pressure change of 21.5 megapascal to compress 1 unit volume of water just to result 1% change in volume. So it will take 21.5 megapascal to change 1% volume of water. Therefore, most liquid or all liquid known as incompressible fluid. On the other hand, gases are categorized as compressible fluid. We know the ideal gas law can be written as P equal to density multiplied with R and temperature, where we know R is the ideal gas constant, so that the bulk modulus of elasticity of a gas will depend on the process being applied to that gas itself. So if a process to compress the gas is an isotherm process where the temperature remains constant, we know that the pressure over density will remain constant. So we can write down for isothermal process, the bulk modulus of elasticity of that gas will be pressure change divided by change in density divided by the initial density. And as we know that P per rho is constant, we will only have pressure. So the bulk modulus of elasticity during the isotherm process will equal to the value of pressure itself. Due to the compressibility nature of a fluid, let's say we give a disturbance to that fluid at certain point, then that disturbance will propagate inside that fluid at a certain velocity. These propagations of disturbance inside the fluid can be described as a speed of sound, or we know it as c. Speed of sound is a function of the square root of change in pressure divided by change in density of a liquid. Or for an ideal gas, we normally note down the speed of sound as the square root of K, R, and T, where K is the ratio between Cp and Cv, that is the specific heat at constant pressure to the specific heat at constant volume. Or it can also be written as the ideal gas constant equal to Cp minus Cv.